In this video, we're going to look at using light with ions. Specifically, let's make an ion. So light can hit an electron on an element with enough energy to knock that element free. This was the photoelectric effect, where different wavelengths of light was needed to cause a current to flow when shined on a piece of metal. In our case, we're going to take lithium, we're going to make it lithium plus. This means we're going to go through the first ionization energy. That ionization energy is 520 kilojoules per mole. Take a moment and think about this problem. I've got an atom, I need to hit it with a photon, I need to knock off an electron. How can I use this information to find what wavelength of light would be needed to do that? Technically, what maximum wavelength? Remember, the smaller your wavelength, the more energy you have. When you knock an electron free, you can always give it a little extra energy. Once it's off the atom, when it's broken free, the extra energy just goes into speed. But there's a minimum energy to just knock it off the atom. Using this ionization energy, can you find what wavelength of light would do that? Go ahead and pause, give this a try. All right, well, if you're back, we got lithium. It's got its 3 protons around it and its 1s. It's got 2 electrons. And around that in the 2s, it has 1 electron. And some distance out is the break-free point. We have to hit this electron with enough energy to move it just past that break-free point. This will give us the minimum energy necessary. This is the ionization energy. Any more energy that will go into the speed of that electron, but we want it just that much. We actually know this energy. We know that to do this would be 520 kilojoules per mole. But our photon hits 1 electron. It gets absorbed. So what I really need is the energy per electron. We have to break this down. I know it's 520 kilojoules in 1 mole. And that 1 mole is 6.022 times 10 to the 23 things. So that would be 1 mole of electrons. We will find that is 8.635 times 10 to the negative 22 kilojoules. This is the energy per electron. So it's the energy for 1 electron to get knocked off. Well, our electrons absorb 1 photon to get excited, knocked all the way off. So this has to be the energy of the photon that electron will absorb. We can convert that to joules. It'll be 8.635 times 10 to the negative 19 joules. Which means I know the energy of my photon. And it's in the units we're going to need, because what was our energy for a photon? The energy of a photon was equal to hc over lambda. I'm trying to find the wavelength, so this is great. I can rearrange. My lambda is hc over the energy of that photon. Planck's constant, 6.626 times 10 negative 34 joule seconds. So we needed it in joules. Speed of light, 3 times 10 to the 8 meters per second. And our energy, 8.635 times 10 to the minus 19 joules. 2.3 times 10 to the negative 7 meters, or 230 nanometers. So what wavelength of light is needed to knock that first electron off lithium and turn it into lithium plus? 230 nanometer wavelength light. Any larger than this, and it wouldn't have sufficient energy to push that electron all the way off. Any smaller, and the extra energy will just go into the speed of the electron. Well, let's try it a little further down, and let's give it a look at going from carbon 2 plus to carbon 3+. In this case, I have an ion already, and we are continuing to ionize it. And so if you have a sample and you blast it, small sample with a bright, intense laser beam, or a light source with all sorts of wavelengths, you can knock the first electron off, a second, and a third. You can keep knocking them off. What would be the wavelength of light needed to knock this electron off? Go ahead and pause, give that a try. Well, if you're back, we are doing the third ionization. We've already lost 2, and we're trying to lose the third. So first, second, we are trying to lose that third electron. So 4,620 kilojoules. 4,620 kilojoules would be our energy. 6.022 times 10 to the 23 in 1 mole. 7.67 times 10 to the minus 21 kilojoules. Or 7.67 times 10 to negative 18 joules. So we have our energy. We can plug it in here in place of our previous energy. Hc over our new energy will be our new lambda. Lambda will be 2.59 times 10 to the minus 8 meters, or 25.9 nanometers. If we think about the values for a second, between lithium going to lithium plus and carbon 2 plus going to carbon 3 plus, we're about 1/10 the wavelength, which means we should be about 10 times the energy. If we look at our values, 8.6, 10 minus 22, near enough 8 times 10 to the minus 21, we're about 10 times more energy. And if we look at our values just in the table, 0.5 versus 4.6, pretty close to 10 times more. And so it seems to be holding up roughly with our calculations. Well, that's if you want to create an ion by hitting an object with light in order to knock the electron free. But what if I've got fluorine? It has some orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9. And there's one more electron floating out here past free. It's going to come in and it's going to drop and go to the lowest energy orbital it can. Now it's possible to bounce along the way, but we're going to assume that it's going to drop from free all the way down. If that's the case, what wavelength of light would be given off? So we're going to emit a photon to get rid of that energy. Can you find what wavelength we expect that to be? And this table is in kilojoules per mole. Go ahead and pause and see if you can determine what that wavelength of light emitted would be. Well, if you're back, we have 328 kilojoules per mole. And again, 1 mole, 6.022 times 10 to the 23. How much energy is given off per electron? We'll find that it is 5.45 times 10 to the minus 19 joules. Went ahead and converted us to joules here. Let me find the energy that's given off for it. Well, lambda's going to equal Hc over energy again. 3.65 times 10 to the minus 7 meters, or 365 nanometers. In this case, this light is going to be given off as the electron relaxes and goes down to fill that orbital and become an anion. As electrons jump between orbitals or breaking free or coming from free electrons to being on an orbital, these transitions have an energy associated per electron, and that energy is, more often than not, emitted or absorbed as a photon. And so we can calculate out the energy of that photon and determine what wavelength of light we would expect to make that happen.